Good afternoon.
Good afternoon, this is Iouri. Can you hear me?
Yes, I can, Iouri. How are you doing?
Good, good. How are you?
Good, thank you. I'm just going to give it 2 more minutes and then we will start. Can you see my screen, Iouri?
Yes, I can.
Good, thank you. Good afternoon to all. It's 1:31 and I would like to welcome you all to today's webinar. My name is Janneke van der Zee. I'm the Managing Director of ITS Canada. On behalf of the Chair of the CAV Technical Committee of ITS Canada, Professor Dave Michelson, I welcome you all to today's webinar with guest presenter Iouri Nemirovski. The plan is for Iouri to present for about 45 minutes. And during the presentation, you are more than welcome to type in your questions in the question box that you can see on your control panel. After Iouri's presentation, we will allow approximately 15 minutes for Q&A. And then at 2 o'clock, we'll end this webinar. For anybody whose questions did not get answered, we'll make sure that Iouri receives your questions via email and can follow up. The plan is to record today's webinar, and the webinar recording, including the presentation with Iouri's permission, will be featured on ITS Canada's website. Just going to introduce Iouri. Just going to read his bio and then we'll change screens where we will make Iouri the presenter. Iouri has a strong background in roadside units and onboard automobile devices, system development, and connected vehicle device standards, applications, and deployments both in hardware and software. He has extensive experience in the development and implementation of signal phase and timing, emergency vehicle prioritization, and RSU deployments. Iouri leads a team of engineers defining our ongoing V2X and V2V solutions in the US. Based in Austin, Texas, he works with Siemens project management, product line managers, systems engineers, and subject matter experts to ensure each CV project is meeting the client needs with innovative solutions. He was part of the successful team implementing the USDOT Tampa-Hillsborough Expressway Authority CV project, is the Siemens project manager for the USDOT pilot in New York City. Iouri has an MS Engineering from Moscow Aviation University and is a PMP and a Six Sigma Black Belt. Iouri, I'm going to hand over my screen to you.
Okay. Can you see my screen?
Yes, thank you.
Okay. Excellent. Yannick, thank you very much for introduction. I'm a product manager for connected vehicle applications for the North America operation of Siemens Intelligent Traffic Systems. So in those 45 minutes, I'll try to cover as much as I can, sharing our experience working with connected vehicle applications and deployments. I'm going to try to cover connected vehicle basics, SCMS, the secure certificate management system, connected vehicle applications, RSU basics, and some lessons we learned in deploying USDOT pilots. First of all, a little bit of history. The actual connected vehicle process started in 1984. It's pretty long process, as we can see. So in 99, FCC allocated 5.9 gigahertz spectrum specifically to safety ITS applications. And then throughout that period, there's more research was done, and about 2015, the first pilots started. USDOT pilots. Currently, there's 3 pilots, USDOT pilots. There's other projects and deployments, but the USDOT pilots are Wyoming, Tampa, Florida, and New York City. So the Tampa, Florida started 2015, and New York City started in 2016. We started working with them in 2018. So throughout this whole path, there was ups and downs, and everybody expected in roughly 2016 that there would be some kind of mandate from the USDOT to start using the connected vehicle devices in the all new cars. Well, as we all know, that didn't happen with the new administration. It's kind of hands-off approach to the technology topics, letting the market to decide what's going to end up being the solution for the safety and traffic management issues on the road. So even though several car automakers still are planning to implement the connected vehicle devices, we all know that General Motors has been equipping STS Cadillacs with onboard units for a while now, from 2017. Then Volkswagen is planning to put the onboard units with all new Golf 8 vehicles starting next year. So there's multiple connected vehicle projects throughout the United States. On the left side, you can see the map from USDOT. You can see it on, I think it's called traffic.gov. That lists all of the current and planning connected vehicle project in the United States. The map is, it says it was updated in September. I don't see actually all the projects, at least that we know of, but it pretty much shows the status. So you can see that some states are much more interested in putting the pilots and test implementation than others. We know Michigan is one of the leaders, Ohio, Florida. That's where a lot of projects are currently started or being planned. On the right side, you can see Siemens project. So if you can overlap, we can see that we actually have pretty good representation, most of the areas where projects are being deployed, and we have good understanding in the challenges of the connected vehicle deployments. On the bottom of the USDOT map, you can actually see the number of projects, devices installed in the cars, and infrastructure devices. So even though it looks like it's pretty good numbers, 18,700 onboard units and about 7,000 roadside units, but in the reality, of course, it's a very, very beginning. You know, we know that there's millions and millions of cars on the road, and there is probably about 500,000 intersection and road crossing that they can be equipped with infrastructure devices. So we're really in the very beginning of this process. Let's talk about a little bit of the connected vehicle or technologies. So there is a current technology called DSRC, so dedicated short range communication. It's based on the VLAN or 802.11, the same as Wi-Fi technology, but it was specifically adapted to the fast-moving object. So it's 802.11p. It has a low latency, which is very important for safety applications. It does not require any type of access points or routers, so it's not dependent on infrastructure. It's a broadcast and point-to-point. It is specifically was developed for V2V, V2I applications, and commercial modules been available for many years. And the price-wise, the price is very low compared to other type of devices. So now there is other type of technology. Meanwhile, because it took so long for a connected vehicle to DSRC specifically to take hold. Meanwhile, there is another technology that appeared called cellular V2X or CV2X, which is based on the offshoot or spin-off of LTE, which is called PC5 or Sidelink. It is nothing to do with also network-based LTE, so it is as DSRC is point-to-point. It's a broadcast. It uses same frequency range as DSRC. Unfortunately, it's not compatible. It's neither in medium access control protocols or any type of messaging on that level, on the physical layer. And it is relatively new, so commercial modules are not really available yet. There's several manufacturers that provide them based on the Qualcomm chipset, but working with that, we know they close, but there's really no production quality and quantities available on the market currently. Reliability not proven yet because there was no time to implement any large-scale projects, and the technology relatively new, so there is no really proof for that. Other than that, they really provide very similar applications as DSRC. Actually, application side is supposed to be doing exactly the same. So it's two technologies that that cover physical layer. So for example, if we look at the layers of the protocol stack, so we look at an example with the WAVE protocol, which is DSRC, another name for DSRC. DSRC mostly related to hardware and Spectrum, WAVE related to the software applications. So you can see it's application layer. So on the bottom is a physical layer. In this case, it's a layer for DSRC type of applications, WAVE. And there is a network layer and application layer. So in case of CV2X, the physical layer is completely different, so not compatible with DSRC. However, the upper layers, the network layer and application layer, supposedly are the same. So if you can implement your interface from physical layer to network layer, the rest of the message is supposed to work very similar. From the frequency allocation, generally speaking, there is so you can see on the left, there is a ITS G5, what it's called in Europe, and what's called WAVE in North America. This is where the traffic safety efficiency. This is the part that was in 1999 that FCC allocated specifically for WAVE applications for DSRC. And then on the other side, there's a Wi-Fi. So currently there is two discussions, we call them discussions, I guess, that continues at FCC. So on one side, the companies who are providing Wi-Fi and other communication are actually saying that the spectrum was specifically dedicated in 1999, being there was a little use for that. The application is still not deployed, so they want to basically auction off that part so they can put Wi-Fi devices in the same spectrum. On the other side, there is discussion between DSRC and CV2X. So currently only DSRC are allowed in that spectrum. Any other devices that could be used there, but they have to vacate the spectrum as soon as they become interfere with DSRC applications. For example, we had in Tampa now, one of the projects, we had actually a device that was broadcasting information on the same spectrum. So we had to approach FCC, and after lengthy discussions, that device vacated the frequency. So in order for example, for CV2X project to use the same frequency, they have to get special experimental license from FCC. While DSRC and OBU don't need any license, but RSUs, actually there is a standard process of applying for a license for specific location for each RSU being deployed. So currently there is a discussion. This discussion actually really prevented a lot of companies, car companies, specifically you can say it, Toyota, who was supposed to start putting onboard units in their cars in 2022 model year. They recently came out with a statement saying unless there's a clarity from FCC how the spectrum going to be used, they will have to postpone it. So there's a lot of pressure on FCC from multiple sides, from most of the car companies, of course, support to have this DSRC or that spectrum being reserved specifically for safety applications. Also, between car companies, there is a pretty sizable split between car companies that support DSRC, which is General Motors and Toyota in North America, and in Volkswagen Group in Europe. And on one side, on DSRC side, and on CV2X side in US, it's Ford and BMW in Europe. So everybody is expecting some kind of guidance solution in FCC, and there is indication that might even come this year, but we'll see. So we can look at the communication, and since basically all of the pilots and projects, connected vehicle projects in the United States are DSRC based, with the exception of the Colorado project, I will cover this connected vehicle from DSRC point of view. So it is 5.9 gigahertz frequency band. It is licensed for OBUs, but you have to receive a license for roadside unit. It is dedicated for traffic applications. It's end-to-end communication real time with a high vehicle velocity, so the latency is extremely low. And it's a multi-channel operation, so using multiplexing. So basically it means you can use different services and different channels. So there's currently this spectrum, which is total of 75 megahertz. There's 7 channels, and there's one channel 179, which is control channels, which used to tell onboard units what type of applications are being running from roadside units, and for example, or how to connect to specific services using so-called WSA wave service advertisement messages. The other channels are used for specific applications. Channel 172 is specifically used for safety applications. So the basic safety message, the core message for the connected vehicle applications is transmitted on channel 172, as well as map and signal phasing timing from the intersections. On the other side, there is a channel 184 that's used for high power communication for public safety. As far as I know, none of the connected vehicle projects in the United States using this channel. The rest of the channels can be used for different applications. For example, for some kind of messages for road safety or road conditions, can be used for uploading information from the onboard units, downloading new firmware to the onboard units, and other type of applications. So as I mentioned before, it is a multiplex, so the radio can share different channels. So it is based on 50 milliseconds time slots. So most of them, or they should connected vehicle devices, onboard units and roadside units, they should have 2 radios. It means one radio can work either in continuous mode, and another radio can use 2 different channels. So anywhere from 2 channels to 4 channels can be used by signal connected vehicle device. So it's generally a rule that channel 172, which is a safety channel, is running continuous. So devices are listening and sending information on that radio continuously, while the other channels can be split in two. So one can be, for example, sending information to WSA messages, what to do for the roadside units, sending to onboard units, what to channel to listen to for some other applications, and also sending, for example, firmware upgrades on the different application, on different channel. So this is exactly why the GPS accuracy is quite important, not only for onboard units where a lot of applications based on accuracy, lane matching, or where exactly vehicles are in relation to each other, but also for roadside units. Even though positioning is not important for roadside units, generally speaking, but the time synchronization with the GPS is very important, because that's the way onboard units and roadside units can listen to different slots of the same radio. They have to be synchronized to know when radio switches from one channel to another channel. So if, for example, roadside units loses synchronization, then it basically will lead that they'll have to eventually stop sending messages. So basic message from the more or less the lower level of the messaging is called wave short message. WSM, and this basically includes what is called PSAD, which is the indicator for the applications running on the upper level, what type of message is receiving. So there is IEEE actually manages this these PSADs. So different type of messages, different PSADs. Also, there's some that based on standards, and also some that can be organizations can apply for their own PSAD. For example, Siemens has 2 messages over the year and data log transfer for Tampa, and New York City has its own messages being specified. So as long as they are being recorded by IEEE, that they can be used. So channels can be configured different ways. I mentioned in our case, we have a default settings. Basically, 172 is constantly continuous, 178, which is a control channel on slot 0 timing, and 176, that's team messages, and then other messages can be sent in slot 1. But also it's dictated by the type of applications. For example, in New York City, it depends what this particular roadside unit is supposed to do. It can have completely different set of channel assignments. Several slides on security credential management system. So of course, it's all nice and good sending all this information back and forth between vehicles and infrastructure, and between multiple vehicles. However, the biggest problem, of course, in this case, it's privacy and integrity. Somehow all this information needs to be secure. And that's the reason for security credential management system. So basically, devices needs to trust to each other, one side, and also they have to use encryption and signature keys, so they can actually talk to each other. So the security credential management system is more or less a privately run system. It's not only one. There is at least, I think, 4 different providers right now that projects can use, and they provide integrity, privacy, and interoperability between different devices. So basically, there is several steps that each device needs to take to, in order to become part of this SCMS system. So first of all, the units have to be enrolled. In this case, RSU. So it's a kind of passport for the whole system that that particular device can be used in the system. So there's multiple steps how to get there. So original was that some of the organizations such as Omniair, which is a consortium that comprises different companies, test laboratories, vendors, that they would actually test and certify devices as being compatible. And then in this case, they can be enrolled into the SCMS system being used there. But anyway, so it is, I think, in progress. There is a different type of levels right now of the certificates. There is a test certificates for different type of plugfests or project that don't really use that much of the security, but also all the pilots are in the pilot level or basically very close to production level system that are very secure. So there is enrollment. So first step, the unit is to be enrolled, and it should be done at the factory or where the devices are being configured by the vendor. Then they can be sent to the site, and once they're being installed, they contact SCMS and upload and download, let's say, upload different type of certificates. So Roadside units generally using application certificates. This is basically they're being uploaded or what is called topped off every week. So unit connects to the SCMS and gets new certificates every week, and they have 1 week overlap for. So in case there is no connection, so they can still run for another week. Onboard units use a called pseudonym certificates, and the pseudonym certificates actually they in addition to being you can use it for signing messages, they also use to prevent anybody to actually discovering whose unit it is. So they in general downloading 20 certificates every week, and they being constantly rotated. And roughly, I think, several minutes, and also depends on the distance. So the reason for that, so nobody can actually track the particular vehicle. So in addition to that, there is a misbehavior detection and certificate revocation list functionality is being developed as we speak by US DOT. Several companies actually participating in testing. So the idea is you want to detect either misbehaving or unit that has some kind of functional problems. So roughly speaking, there is there's a way of reading the information that's coming off of the unit, verifying if the positioning does make sense, or speed makes sense, or acceleration, heading, and then detecting the units that actually do not meet the requirements. For example, if you are a CU and you're detecting the unit with coordinates 10 miles away from where the roadside unit is, it's definitely not plausible. So it's either something wrong with the units, or it was hijacked and being used for some kind of malicious reasons. So once once information is collected, either on OBU, on RSU, the report being sent to CMS, and then based on that, either unit is blacklisted, so that means the enrollment is being canceled, so they cannot get any more other certificates, or in case of application certificates or the pseudonym certificates, the revocation list is being sent down to the unit, so then everybody knows that that particular unit on the list cannot be trusted, so it will be ignored every time it's being seen. Messages and applications. So all the messages which is running basic all the way through the communication stack, all the way up to the application layer are specified by SAE J2735 standard. There is 17 messages totally described in this standard. They divided in frames, data elements, and so on. And some objects are mandatory, some are optional. So the issue right now is, even though, as I mentioned before, there are organizations like Omniair that certify units based on the interoperability and compatibility of all the communication stack to the requirements, specifically in RSU, it's called RSU 4.1, USDOT RSU 4.1 spec. However, there is no really testing right now on the application layer. So some objects can be mandatory, some optional. even though they're described in the specification, they can be really interpreted different way by a vendor who's developing this type of devices. So I think the next step is very important, is actually testing these devices in interoperability and application level in addition to the communication level. And this is where I guess there's a little difference between European approach and US approach. So in the US, the emphasis was on the interoperability and the communication layer, not so much on application. So US has, as I mentioned, certification program, which Europe still doesn't have any. Wherever in Europe, the emphasis was actually on the compatibility on the application level. So the corridors that being project that being basically corridors from multiple countries throughout Europe, where the idea is you should be able to drive through that corridor from, I don't know, from Denmark to Greece, and be able to actually be able to communicate, not only communicate, but actually interpret the applications being deployed throughout the corridor the same way. But I think there is actually convergence of both two approaches currently happening right now. So I know that Europe is working on defining the certification process, while in the US there are several organizations that are working on the application level testing. One thing is, one message is not equal one application. So you can see there's different messages listed, specifying the J2735, and multiple messages can actually be used in multiple applications. So the core message, basic safety message, is used in emergency electronic brake light, forward collision warning, do not pass warning, intersection movement assist, and so on. So basically it's not one-to-one. The messages are kind of source of information, the applications, how to use that information in order to either make traffic safer or more manageable. As I mentioned before, there's all this list of DSRC messages in 2735 standard. The main ones actually is a basic safety message, map data, personal safety message, which is similar to basic safety message, but specifically for preventing collision between pedestrian and vehicles. Signal phase and timing. This is what the controller, traffic controller, sends to the vehicles. Signal request message and signal status message used in preemption and priority applications, and travel information message used basically sending the status of the road and any other messages that are required. So all of these messages more or less driving all these applications, so provide information for all these multiple applications, which are generally consists of two groups. One is V2V, which is vehicle to vehicle, and those do not require any type of infrastructure devices. So do not pass warning, emergency brake, forward collision warning. All you need to do is basically two vehicles, or maybe three vehicles in the case of do not pass warning, that actually located next to each other and then talk to each other. V2I applications, that's the vehicle to infrastructure. This is where the vehicle actually need, or at least communicate to infrastructure equipment. In most of the cases, roadside unit that provides information, for example, for the curve speed warning, or of course all of the type of information with timing of intersection is required, or actually map of the intersection is required, preemption, priority, and so on. There are some of the examples of the V2I, for example, application, time to change. So this is for provides timing of the intersection change to the next phase. So the vehicle that approaches the intersection knows how long it takes to the next phase, and can be used to avoid necessary stops and improve energy efficiency for the vehicles. It also, for example, it's being used in many pilots right now for autonomous shuttles. That's how they know where to stop at the intersections. Either use cameras, or in addition to that, or just basically using just a SPAT message. Wrong way entry based on the map message, so the car knows if it enters a lane which actually has a defined direction which is opposite to the direction of the car, and then is being warned. There is an extension of this message. If there is for example, a detector, an external detector that detects a car that's moving in the wrong direction, it can also send a message to other cars saying there is a car, wrong way driver on the road, to warn them. Red light violation is more or less similar to time to change, except the car actually knows how long what's the standard current phase of the intersection of the its approaches to, and the car can calculate if using the same speed or acceleration, it actually run the red light and actually warn the driver, or it can slow down the car automatically in the future applications. Speed limit warning, it's a more or less warning sent to the vehicle, either for a regulatory warning or just in case the vehicle exceeding the speed limit. There's emergency vehicle preemption and transit signal priority, very similar from the connected vehicle point of view applications. They are more or less getting vehicles requesting information and request to pass the intersection, to change the timing, and it's getting reply back from the intersection saying allowed or not allowed. Work zone warning can be used in, for example, movable or trailer. You can place the RSU on the trailer and then place it in some location where the work zone started and send the messages, or the intersection, if it's within this multiple intersection, can send that information to the vehicle. Curve speed warning, very similar to the speed limit, except that it can actually add smartness to it. For example, for the queue that builds up outside the visible part of the road, and so actually you can change the speed based on the side of the queue. V2V application, intersection movement assist, with the two cars actually crossing the intersection at the same time. Do not pass warning, warning the car that there is somebody in the opposite lane. Emergency electronic brake light warning, very useful on the highway, for example. So when the car brakes hard, it's the text that sends the message to the other cars, and it could be 4 or 5 cars in front of you. You don't see that actual event happening, but you get warned. And forward collision warning is basically more or less the same thing that current cars with the sensors have, but it's an additional layer of safety if somebody brakes right in front of you. A couple words about what these main elements of these messages are. So first of all, map, and it's provide geometric layout of intersection. So really, there's a tools. USDOT has a tool. Some vendors have their own tools. Some integrators have their own tools. The whole idea, you're building the map of intersection based on the position of the intersection and some kind of map. It could be Google Map. It could be Bing. So you have to provide what type of approaches there and how they link to maneuvers and restrictions of where each lane can connect to. One of the example application, wrong way, if you're entering the lane that actually is a egress lane, then you get a warning from this from the vehicle. SPAT, signal phase and timing. As it is, this information is coming from the controller. It is linked to the map always. So the map has ID, and the signal phase and timing has to match that ID, so it understands that actually it fits that particular intersection. And the reason is, especially in urban conditions, so there is multiple intersections, and most of the time the cars actually can get information from multiple RSUs. So it has to know what timing corresponds to what intersection. Otherwise, it will think that it's passing this. The timing comes from an intersection, actually coming from some other one. So it's actually important when you configure to make sure that the ID is actually matching with each other. And it's what it uses for. It uses status of traffic controller. It's a signal status current and prediction remaining time until it changes to another one. Using red light violation, time to green, time to change, green light optimal speed advisory, right turn assist, left turn assist type of applications. TEAM as a travel information message is used broadcast to convey road conditions and speed messages. It also uses ITS phrases, the same ones that use for, they're between the different signs. Each of them has a code, so you can put the message in the ITS code in the message, and the vehicle will understand which type of warning it is supposed to be. And if there is a HMI, it actually will show the corresponding image if it's programmed accordingly. It also has start time and duration of the message. You can specify this particular, for example, a school speed zone warning. So for example, it can program it that it can only run to specific time, and it affects specific region. So, you know, even though that vehicles can receive it from a relatively large area, it can only be specified specific position on a specific road. Used for variable speed limits, curve speed warning, work zone warning, and similar applications. Just a couple more about how the time to change and what you need to know how to configure it. So time to change, again, it's come from the traffic controller, ATC, using interfaces, for example, V2I hub. There is a new NTCIP 1202 standard that has to do with the messages or objects description for a controller, for traffic controller. So there is it's coming, version 3 is coming up, and there at least 2 different protocols are allowed. One of them V2I hub, and basically the controller sends information to roadside units, or roadside units pulls it, or it can be sent by ATC, depends, through NTCIP, and then or in this case it's through UDP packet, and it converts it into SPET message and sends it to onboard units. So the most important thing is, as I mentioned before, is we need to make sure that the ATC actually meets the requirements of the protocol, and it normally does. Most of them do. Countdown only works when the fixed time controller settings. Right now, so it has to be fixed, or for example, if it's detector based or there is a call placed by detector, it will reset the timing. So you will be driving to an intersection and see a certain countdown to end of green, and then on that side street there would be a call, and then it changed the timing. So that's still have to be worked in to get this actually usable. And if you use even more complex ways of creating timing on the intersection, then most likely in the future type of AI would be needed to actually predict the timing on each phase. We need to ensure that I mentioned before, the map is the same ID as a SPET message. Speed limit warning using team message, basically being created on either TMC or an RSU. Most makes sense to create at the TMC in central location, is so you can, for example, create special conditions for example, ice or wind or rain, and send it to vehicles to warn them. A little bit about roadside units. So this particular page shows Siemens roadside units. There's a multiple you can get from multiple vendor units. What you have to, I think, pay attention when you order a unit, it's their capabilities. So the CPU and the amount of memory should be sufficient. There's different ways of different vendors approaching connected vehicle, where applications should be running. Some, like we, for example, we prefer to run them on the roadside unit. Some other prefer to run them on the controller side. So it's a different approach. However, there's plenty of applications that that can be, RSU can be placed in where there is no traffic controller. For example, it's on the highway and ramps. It could be somewhere mid-block for the pedestrian safety application and so on. So you need to make sure that what you have is actually meets your requirements. On interfaces, it's always have to have better to have more interfaces. For example, in addition to the standard DSRC or Ethernet, to have ability to Wi-Fi and Bluetooth, because you can actually use the RSU unit for travel time calculation, where you would have to buy a separate device, but they can use RSU in place of it. So maybe you don't have a specific budget for connected vehicle test pilots or anything like that, but you need to buy equipment for travel time. You can actually combine it together and use it for testing and connected vehicle application, also for the whatever you originally planned to use for. So the connection, normally you would have basically, it's required to have that on board. The roadside units are power supplied by power over Ethernet. It's specified in 4.1 requirement, USDOT RSU 4.1. So you can connect controller directly to it, or you can connect it through the PoE injector. If you have multiple ports, you can control your programming station through the switch, or for example, in our case, there's another port, Ethernet one, that is a JCP, and you can connect the device directly to it. A little bit about our experience, what we learned in connected vehicle deployments. So as I mentioned before, there are three, in addition to other projects, there are three US DOT pilots: Wyoming, Tampa, Florida, and New York City. It was on purpose completely different projects. So Wyoming is open road, there is no intersections, there's mostly V2V applications and applications based on team messages to warn about ice or wind and so on. There's a Tampa, which is medium-sized urban area, mostly the idea was to test different type of scenarios or use cases and applications. And so the majority of the cities in North America will be falling into the type of Tampa project. And of course, there is a New York City, which is more or less the purpose of this project is to understand if the connected vehicle applications can be used in environment or heavy urban environment with the positioning challenges, with the urban canyons, and all the type of interactions that you get from construction, from a lot of devices deployed there from different frequencies and so on. So if I look at the connected vehicle project at Tampa, so Siemens supply equipment, and in case of Tampa also back office system on New York City and Tampa. Tampa is, it has about 1,000 privately owned vehicles. It includes mid-block pedestrian safety, 10 trolleys, and 10 buses running TSP, which is priority. So the idea was you can define your use cases. For example, one area was rush hour collision avoidance. Then the traffic management for the other part of the area. There is a pedestrian safety part of this downtown that is being deployed. And based on that, different type of applications were used. So for example, this is what you see all the way on the left side. You can see the locations, the need, what is needed to be done. For example, wrong way entry on the highway that coming into the city and in the morning and leaving the city from other directions. So you need to make sure there is no cars going wrong way on that road. So there is backups in the morning in different locations. So based on this, the application where each use case combined multiple applications that grouped in different safety, mobility, and agency data categories. So that's basically approach to the project. You want to make sure that you define your use case, and from there you understand what type of applications you want to apply. What lessons we'll learn from it? First of all, you need to invest time in ConOps requirements. Because in the beginning, there was a lot of requirements that actually at the end didn't make any sense. So you have to be, your team, your stakeholder team needs to be very flexible, understanding what is actually the needs. Do you need those requirements so you can actually concentrate on the right ones? You need to select reliable partners, vendors. So again, everybody expected there was a mandate, several years ago. So a lot of companies entered that market who didn't really have much experience. It could be a lot of startups. So none of them actually had enough resources to go through all the projects. So you need to make sure that in addition to the price, you have to make sure that you select reliable vendors. You need to integrate it with infrastructure experience. A lot of this, I mentioned, companies had either automotive or maybe some kind of university background when they started. So they had to make sure that the company who's integrating the system together has a lot of knowledge of the infrastructure. I mean, one example, to get the permit for installing an RSU, to get the power, to get everything, and have all the documentation done. The people who actually work in this type of environment, from the citizens, it might take very long time. You need to understand how you connect your backup system. So if you have 2 or 3 RSUs, maybe it's not a big deal, but you have 100 of vehicles and 50 RSUs, you cannot go and manage them one by one. You need to have a back office system. For example, Siemens has one of those systems called Concert. There's another vendors who have different type of systems. So you can actually download, upload, look to the status of the roadside units and onboard units as well. The OTA, so over-the-air update, needs to be as well very important, because once you put the cars there, it's very difficult to bring them back. We have only a minute left, so I will talk about New York City. Of course, is the most challenging project probably in the world. One of the biggest ones, probably if not the biggest. It's a 550 RSUs, about 7,000 aftermarket safety devices, or OBUs, covering Manhattan and part of the Brooklyn and 2 airports. Most of the project, actually, the goal of the project is this technology can be actually used in a densely populated urban area. There's several applications deployed, but the main thing is actually, so can it actually work there at all? Lesson learned, again, select reliable partners, vendors, manage project team. You have to understand that a lot of times the partners or vendors are actually at the same time competitors. It rarely happens on a standard ITS project, but it always happens, or many times happens on connected vehicle projects. Cybersecurity is extremely important, especially in the cities that have its own very strict IT rules. If you're integrating OBU in the CAN bus in the vehicles, you have to keep in mind that a lot of models and different manufacturers of the cars has completely different understanding of what information and what part of the CAN message is. And GPS accuracy limitations, always limitation, especially in places like New York, but also another one. So there is a limitation currently about 1.5 meter for I think 67% of time. So some applications work no problem with that, but some actually, if you need to match lane on a smaller road, you might have an issue actually getting that correctly. And test units before deploying. That's my presentation. Again, try to put everything in 46 minutes. It's not that easy, but again, open for any questions, and any follow-up questions, I can definitely try to answer them.
Thank you very much, Iouri. So we've received a couple of questions. I'm just gonna, James is wondering, you might want to consider the new IEEE 802.11 BD update by DSRC. It provides the modern radio performance benefits of LTE PCS with the advantage that it has same channel coexistence and backwards compatibility with 802.11p.
Absolutely. So everybody has a different opinion about this, but I'm personally I like the approach that Toyota has. They believe that the DSRC at this point is the only proven protocol that's been for the years and years of testing. From our point of view, from Siemens, we agnostic from the point of view of platform, but as a manufacturer of the infrastructure equipment, we need to make sure that it's tested and reliable. And yeah, the new version of 8211 is backward compatible, which C-V2X is still not clear how is it backward compatible, especially with the moving forward to at some point to 5G. It's not that easy.
Thank you. Is there any discussion if the red light or speed warnings will allow for enforcement by police?
Generally speaking, the privacy is one of the major concerns here. So the ideas of constantly rotating IDs, basically it's the privacy issue concerns might be able to kill the whole system if it's not trusted. So to be honest with you, I don't think that using in law enforcement in these general applications are actually will work. There's other applications, enforcement specifically for the buses, for example, and so on. That does not include privacy. That is maybe possible.
Thank you. Doug is wondering, how does time to change green to red time get reported for actuated traffic signals?
Well, that's where the problem is. So it would be depending on how the controller actually, different controller manufacturers do it a little bit differently. There's no really standard how to do that. However, it's a concern because say if it's actuated, then it's going to change the time. So there is other ways of doing this, basically, you have to predict with specific certainty. And there is in the message, actually, there is a certainty information to the roadside units and to onboard units how trustful is that particular countdown is. But yes, the actuated and also predictive type of control is an issue right now.
What is the impact on countdown handled by OTU?
OTU?
Yeah, I'm reading the question. I don't know what an OTU is. Maybe that particular person who submitted that, Doug, can clarify what an OTU is. I'm not seeing that anything. Somebody says, thank you so much for your presentation. Oh, sorry, it's OBU. Sorry, OBU.
Okay.
Yes.
Can you repeat the question?
Yes. What is the impact on countdown handled by OBU?
If I understand, the question is what the OBU was supposed to do in this case of receiving. So really, at this point, the countdown applications more or less as a demo applications to show that how the system actually works, how the timing information will be provided. But there's a couple applications that can actually use this information. For example, the red light violation. So you can calculate how much time it has to reach the stop line, and then it matches if it reaches it at the red phase. So that's one. Is also green wave. So for more advanced cars with partial automation in it or full automation sometimes in the future, that's how they would know how to regulate the speed to be able to reach stay in the green wave.
Thank you. Is there any cost or benefit analysis on reporting of environmental information?
To be honest with you, I don't know of any. I'm pretty sure there's several applications in Europe being implemented, for example, for the timing, the intersection timing or time to change, to minimize amount of time that cars actually stay at the red light and the engine running for nothing, basically. I can try to find out from our colleagues at headquarters if there is anything. In US, I'm not aware of any, at least personally.
Okay, thank you very much. Paul is asking, could you say something more about GPS accuracy required for pedestrian detection? Because this is a big issue for CVs in pedestrianized city centers.
Yes. So, for example, in Tampa, originally we actually implemented mid-block pedestrian safety using LiDAR, which is tracking pedestrians across the crossing. So, original idea was actually to equip pedestrians with phones that would be able to receive the information that warning them that they're approaching cars. However, the accuracy of this personal device at this point are not even anywhere close to the ability to use them as a safety devices. Even a simple application like using the phone to push the button at the crossing to set up the call to the intersection, even that is not accurate enough. It works most of the time, but not every time. So right now the pedestrian safety more or less is actually correctly tracking the pedestrian through the crossing and send that information to the car using personal safety message. In this case, that is correct. This is precise information, and the car knows more or less its own heading and speed, and that it calculates the potential collision, and that can be used to warn the driver. Warning the pedestrian at this point is very challenging.
Thank you very much. Those are all, sorry, there is one more question, and that's the last question. Can you comment on the effectiveness in connection of smartphones to Wi-Fi at RSSU?
I assume RSU, this roadside units. So that was kind of example that I gave before. We have the applications, and not only us to do, you can have a phone that can connect in the area of the roadside unit that's using Wi-Fi. It can connect to the Wi-Fi and get information from the roadside units. This is not really a particular issue with that. Again, the only issue with that is the accuracy of the phone. For example, if you're trying to cross the street, you need to indicate which direction you're going to cross the street. So you need to point, you need to use your phone with the heading sensor to which direction they're going to go. Heading is normally on the phones are relatively accurate, so you can point in the direction. But what happens if you, for example, this time that you're pushing the button, somehow you turned? So now you actually thinking you're crossing that direction, and you give countdown on the phone, but in reality you're not. So there's always limitations to that, but the connection actually between the unit using Wi-Fi and the roadside unit and personal device it's technological is not an issue. It's applications, how to use that connection safely.
Thank you for answering all those questions. I'm going to switch screen to my screen right now. And I wanted to give a thank you to Sadi Mali from Electromega, who has been the co-organizer of this webinar. So thank you very much. Can everybody see my screen?
Yes.
So I just wanted to provide a little bit of an overview of ITS Canada's technical committees. We have 4 technical committees: the Advanced Public Transit Technical Committee, chaired by Brendan Hemley; ITS Canada's Advanced Traveler Information System Technical Committee, chaired by Patrick Fitzhenry, Vice Chair Judy Yu; the Advanced Traffic Management System Technical Committee, chaired by Jonathan Darton, Vice Chair Jonathan Ford; and then the Connected Vehicles and Automated Vehicles Technical Committee, which is chaired by Professor David Michelson; and the International Business Development Committee, chaired by Joe Lamb. And if anybody is interested to receive more information about these technical committees, you can visit the ITS Canada website at www.itscanada.ca. For those who don't know, and I think most of you do know, ITS Canada, together with the Transportation Association of Canada, are hosting the 2019 Joint Conference and Exhibition come up in Halifax in about 12 days, September 22nd to September 25. We hope to see you all there. And then the other important event coming up is ITS Canada 2020 in Edmonton, Alberta, our annual conference coming up next year, June 14th to June 17th, 2020. I thank you all for your time, and we will post the webinar recording and the presentation on our website. You will be receiving an email from me. And thank you very much again, Iouri. Thanks again, Sadi from Electromega. And I wish you all a great day.
Thank you.